we're going to add vectors that aren't necessarily perpendicular. Yesterday you were given components. You could find the resultant as long as they were perpendicular. Today we're going to look at all the other cases. And I'm going to show you two basic methods for doing that. The first method I'm going to show you is the method of adding vectors using the tip-to-tail method, which works, it's effective, and sometimes it works well. Tomorrow and Thursday we're going to do some applications, and sometimes the tip-to-tail method will be the method of choice. But oftentimes it's more confusing than the other method. We're going to add vectors that are in rectangular form using components, and we're going to add vectors that are in polar form by adding components. That tends to be the less complicated way to add vectors, and that's what we're going to spend most of our time on today. So let's start out with the tip-to-tail method. Yesterday we saw that you can take two vectors and move them around so that they're tip-to-tail, and you can see where the resultant is going to be. That's going to be true for any vectors, not just perpendicular vectors. So here's an example. Suppose we have two vectors. We're going to call them u and v, and we want to add these two together. The first one, u, points off in the direction of the first quadrant. The second vector, v, points off into the second quadrant. We want to add these two together. The tip-to-tail method works really well for approximating your answer, being able to visualize the answer without doing any math. Now we can take this, either one of these two vectors. I'm just going to take this one on the left and I'm going to translate it up so that its tail's at the tip of the second one. It needs to have the same magnitude and same direction, which means it's going to run parallel. And it's going to end somewhere, my art is not perfect, but somewhere up there. That art is really bad actually. Let's try that one more time. Well, that's a little bit better. Just a little bit better. And the resultant is going to be from our starting point to the tip of the ending point, which is going to put you somewhere in the second quadrant. Now, in order to figure out the magnitude of that resultant and its direction, we have to use the law of sines, law of cosines, and properties of triangles based on that picture. That's what we're going to do now. We're going to take a look at an example. That's the principle we're going to apply, but let's do the math behind an example here. Let's take these two vectors and add them. We're going to use the tip-to-tail method. Okay. The first thing you have to do using the tip-to-tail method is that you have to make a sketch. So that first one, 15.6 at 102 degrees. Now the more accurate we do this, the easier it is, though our sketch is still just a sketch. It doesn't have to be precise in order to get a correct result. So 15.6 at 102 degrees. That's going to point just past the positive y-axis with a magnitude of 15.6. Somewhere in this neighborhood. The other vector that we're dealing with, 227 at 350 degrees, going to be a little bit longer in the direction of 350. It's likely to be somewhere down here. Now, where will the resultant of these two vectors point? They're going to point into the first quadrant, okay? Now, we could take the red one and translate it up, or we can take the blue one and translate it over. Ultimately, it does not matter. Just for the sake of consistency, so we're all doing the same thing, let's move the blue one over so that its tail is at the tip of the red one. And it's going to look approximately like that. And at that point, we can sketch in our resultant. Now, we know a few things about these vectors. First of all, we know that the red one, the 15.6, excuse me, the blue one had magnitude 15.6. So we have a triangle here where the blue side is 15.6. The second vector, 22.7 at 350 degrees, is the red one. That one's going to have a magnitude of 22.7. So if you take a look at the triangle that's formed, anytime you add two vectors that are not pointing in the same direction, we're going to have a triangle formed with those two vectors in the resultant. And given the information about the vectors, we can figure out everything we need about this triangle to find out how long the resultant is and where it's located. Now we've got two sides given. What else are we given about this triangle? We know what else? What parts do we know? Do we know this side yet? No, that's the magnitude of the resultant. That's one of the things we want to find. We know some angle measures, but it's going to take some work to pick them out of there. Okay? We know that the 15.6 is at 102 degrees. So from here up to there is 102 degrees. Now, what does that tell us about any of these three angles? Nothing yet. Here's what you need to do. You need to go to one of these three vertices, and typically it's going to be where our two original vectors meet. And think of your Cartesian plane as being located down there, or excuse me, the origin as being located down there for a minute. Okay? Because that's going to provide a reference so that we can figure out what that angle down in that bottom right corner is. Now, we know that up here we'd have a total of 90 degrees. You see what I'm saying there? So this angle in this triangle has got to be less than 90 degrees. How much less? How far is it from here? And again, all I did was slide the origin down here temporarily for a point of reference. How many degrees is it from there up to that blue one? 102, which means it is how far from here to the blue one? That is 12 degrees. I'm going to make a note that that little angle in there is 12 degrees. Okay? Everybody agree with that? Now that doesn't quite tell us our triangle angle measure down in the bottom right corner. But go back to the red one. What angle was formed? The red one was at 350 degrees, which means this angle here is what? Which means this angle here is what? 10 degrees. These are alternate interior angles. So this is 10 degrees. Let's stop there for a minute. Now we can find out the angle between the blue and the red. I'm going to make sure everybody sees it before we go on. Is that okay? There's several different approaches to find the same angle. You might use a different method. Sounds like you are. But ultimately, what is this angle between the blue and red going to turn out to be? 68 degrees. That's what's important. So let's stop there for a minute. Everybody agree that that angle down there is in fact 68 degrees. Okay? All right, well now you've got what scenario with your triangles? We can get rid of all this junk now. Everybody okay with that? We're going to clean that up and get some space here. We don't need any of that anymore. That was just to figure out our angle. And that is the biggest stumbling block with using the tip to tail method, is trying to figure out those angles. We know it's 68 degrees. Now we're home free. Let's call our resultant vector r. So let's find the magnitude. Which law are you going to use to find r? Law of cosines. We know that just the magnitude now, r squared is equal to, this is our reference, 22.7 squared plus 15.6 squared minus 2 times 22.7 times 15.6 cosine of 68. And if you work all that out, you're going to find that r is equal to 22.2. Okay. So we know about our resultant a little bit now. We know that our resultant is going to be 22.2 at. Now we just need to figure out what the angle measure is. Okay, how are we going to figure out that angle measure? Remember, you use what? That's right. Which angle do you want to find, between the purple and the red or between the purple and the blue? The purple and the red. Now that won't be this angle, keep in mind. We have to adjust for the fact that the red one is 10 degrees below the axis. Because ultimately, what do we want? We want this angle right there. That's what's going to go in this slot, the angle relative to the x-axis. So what we will find is, let's find this angle right down here, this entire angle, from red to purple. Let's call that one, get that one out of here. We'll call that one alpha. So now let's use the law of sines. We know that. The black one? Because if we want the direction of this purple vector, direction is always given relative to the x-axis. Our triangle doesn't happen to fall on the x-axis. Does that make sense? So let's use law of sines. We know, what do we know? Sine of 68 over 22.2 equals sine of alpha over 15.6. That'll tell us what our angle alpha is, and you should get 40.6 degrees. Okay, we're almost done. It's 40.6 degrees from the red up to the purple. But how many degrees is it from the red up to the x-axis? That was 10 degrees. So if we take off 10 degrees off of that, we get our angle theta, which is 30.6 degrees. 22.2 at 30.6 degrees, and we're done. We found the resultant. We're set. Questions about the idea? Now, there are a couple of points about this method that I want to make before we go on to the second method, but does the general principle make sense? Okay, tip to tail method. A couple things to note. One, this method is no good if you're adding more than two vectors. Imagine the artistic ability you will need. Here, if you have two vectors that you're adding together, you'll get one resultant, you get a triangle. What shape would you get if you were adding three vectors together? You'd have a vector, some other vector, plus the resultant. You'd end up with maybe a quadrilateral, and it gets messy after that. So we only use this method if there's two vectors. You can use it for more, it's just not convenient at all. And you're always going to need the law of sines or cosines, depending on how the information shakes out, to find the resultant using this method. And probably the biggest downfall of this method is that you always have to have a sketch. It's very difficult to use the tip-to-tail method without making yourself a reasonable picture. And a picture is not necessary using the second method. So we're going to leave that method for now. We'll use it in example tomorrow, but other than that, we're going to tend to favor this second method. Questions so far? Are we all right? Good? Okay. The second method is the method of adding components. It essentially does this. If you take two vectors and you know the x and y components, that is the x and y coordinates of the tip, you can just add up all the x coordinates and you get the x coordinate of your resultant. And if you add up all the y components, you get the y component of the resultant. Now you can see that in this picture from the previous example. Let's just look at the x component. Okay? The blue vector had a slightly negative x component, right? The red vector had a very significant positive x component. So what did the blue vector in the x direction ultimately do to the red one? It pushed it back a little bit. And so the resultant had an x component that was a little bit shorter than the red one. Look at the y component. The blue one had a very significant y component. The red one had a slightly negative y component. So the red one pulls the blue's y component down, and the purple one's y component is a little bit lower than the blue one's was. So their components add together to tell us the components in the resultant. And this is super easy when they're already in rectangular form because it's just using the add button on your calculator. There's nothing to it. All right. I'm going to give these vectors names. It's not necessary, but I'm going to give these some names. First of all, let's call the first vector A. We want to add these up. They're going to give us a resultant vector. We'll call it R. And the resultant vector is going to be the sum of the individual components. So if we add these up, first of all, we add up the x components. The x component will be negative 2.4 plus 8.5 plus 6.4. So we move to the left 2.4 units because of vector A. We move to the right 8.5 units because of vector B, and then we move to the right 6.4 more units because of vector C. Where do we end up? We end up at 12.5 units to the right of where we started. So our resultant moves us to the right 12.5 units. That's the net effect. And then the y components. The vector A moves us up 7. The vector B moves us up 13 more. But then vector C drops us down 9 and leaves us at 11.0. We're done. So the net effect of these vectors is to end up 12.5 units to the right, 11 units up, somewhere in the first quadrant. Now let's go back. We're going to rework this example. We did this one just a minute ago using the tip-to-tail method. We're going to rework this again, but this time we're going to do it using vector components. Well, first of all, we're going to find the x component of the resultant. So what we need to do is we need to find the x component of each of the vectors. Now, how do you find the x component of 15.6 at 102 degrees? (15.6) times cosine of 102 degrees. To that we're going to add, well, let's work that out. If we take that x component, you're going to find that it works out to be negative 3 point. We're going to leave plenty of decimals on these components, negative 3.243. To that we're going to add the x component of our second vector. X component of the first vector is 15.6 times the cosine of 102.3. The x component of the next vector is going to be 22.7 times the cosine of 350 degrees, which turns out to be 22.355. So, the first vector, which pointed off in the second quadrant, moved us a little bit to the left. The second vector, which points heavily towards the fourth quadrant, moved us quite a bit to the right. So the net effect Negative 3.243 plus 22.355 is 19.112. That's the x-coordinate of the tip of our resultant vector. Okay? Now we do the same thing for the y component. We figure out how far up and down we've moved. The y component is going to be 15.6 times the sine of 102 degrees. And if you crunch that out, it turns out to be 15.259. Plus the y component of the second vector is 22.7 times the sine of 350 degrees. That means we move up 15.259 units due to the first vector. The second vector drops us down a little bit, negative 3.942. And so, our resultant, we know the answer, it's just still in rectangular form. Our resultant is 19.112. $11.317. Okay, we'll stop there for a minute. We've got the addition done. Now we just need to put it back in polar form, which is what you did yesterday. Okay, questions about any of those components? No? All right. Well, then let's go ahead and find that. We know that the magnitude of the resultant, r squared, will be 19.112 squared plus 11.317 squared. If you work that out, your resultant turns out to be, it has a magnitude of, anybody care to guess from the example that we already did? 22.2. I'll let you catch your breath for a minute. 22.2 is the magnitude, much to your surprise. And then we need to find the direction of this vector, which better be 30.6 degrees. That's what it better turn out to be. So let's check it out. The tangent of our angle has to be what over what from yesterday? How do you find your angle? Tangent of theta is the y component over the x component. So in this case, that's 11.317 over 19.112. And if you solve that, you end up with 30.6 degrees. And so we're done. Our resultant turns out to be 22.2 at 30.6 degrees. No sketch necessary. It's just a matter of organizing your x components and adding them, your y components and adding them. That tells us our resultant, and then we just need to put it back in polar form. What method do you prefer? This one, absolutely. Okay? This one is similar, but we have several vectors. This method, incidentally, is really the only practical way to add 3 or more vectors together, is to break them into components. Here we have 3 vectors, A, B, and C. We want to find out what our resultant is of these 3 vectors. Okay, well, let's start out by finding the x components. Now, this isn't we're going to be doing the same thing mechanically all the time. So if we want to find the x component here, we're ultimately going to take 6.5 times cosine of 90 degrees. Now think about this one for just a minute. You can do this one without your calculator. This vector is pointing where? Straight up. What's the x component of a vector that's pointing straight up? 0, okay? Well, what's the cosine of 90? 0. So this x component turns out to be 0 plus the x component here, 2.7 times the cosine of 52 degrees. I think you'll find that that works out to be 1.662. And the x component here, 4.8 times the cosine of negative 131 degrees. Now that's pointing off in the second quadrant. That means the x component should be negative. It's pointing off to the left. Minus 3.149. We can add all those together and we've got the x component of our resultant. If you do that, you get negative 1.487. So the net effect is a little bit to the left of the origin. The y component of our resultant. Well, here again, you really don't need your calculator to do the first one. What is the y component of that vector 6.5 pointing straight up? 6.5. It's all in the y direction. Plus 2.7 times the sine of 52 degrees. .128. 4.8 times the sine of negative 131 degrees is negative 3.623. And the net effect in the y direction is positive 5.005. So we move to the left and up for our resultant. Okay. Good? All right, well now we know where our resultant is. We know that the resultant vector in rectangular form is negative 1.487, 5.005. Now it's important to note when you go to get your angle on your calculator later, it's not always, remember, going to tell you the angle in the correct quadrant. So it's important to note that this is in quadrant 2. So later on when we go to find theta, make sure that the calculator gives us an angle in calculator 2 or that we adjust in quadrant 2. Well, our magnitude, r squared, is going to be negative 1.487 squared plus 5.005 squared. Should find that that gives us a resultant of about 5.2. Got one decimal on all the input magnitudes, so we'll keep one on the output magnitude. And finally, our angle. We know that the tangent of theta has got to be the y component of 5.005 over the x component of negative 1.487. Your calculator says that theta is equal to, yep, your calculator says, oh, must be pointing in the fourth quadrant, negative 73.5. Is that correct? That's not the right angle. Your calculator says it's down here, but in fact you are up there. So add 180 degrees. And our true value of theta is equal to 106.5. So we've got our resultant. It is 5.2 at 106.5 degrees. Most of the mistakes that I see in adding vectors are in this case right here, where the resultant is in some quadrant other than what your calculator reports. It's an easy step to forget. Grant? Now, any questions about any of those components or the conversion again? Okay, we're going to wrap up here by combining vectors using scalar multiplication and vector addition. First of all, a very quick review from yesterday. Let's suppose the vector A is 2.75 at 345 degrees. What is negative 2A? Well, it's going to be negative 2 times 2.75 at 345 degrees. But multiplying by a scalar only changes the magnitude. So negative 2 times 2.75 is negative 5.50 at 345 degrees. Now that's true, but we tend to not like negative magnitude. So it's pointing in the opposite direction of 345, which means it's actually pointing at minus 180 degrees from that. 165. Whoops. .50 at 165. We're done. Okay, scalar multiplication, you got to like that. Let's take 638, let's let the vector p equal 638 at 220 degrees. Q equal 315 at 37 degrees. We want to find 3.5p plus 1.5q. The vector 3.5p is going to be 220 degrees. But what's our new magnitude? If we take 3.5 times the magnitude of p, you get 2233. Three and a half times 638. Look good? Okay. To that we're going to add 1.5q, which means we're going to add 1.5 times the magnitude of q, which is 315. And that turns out to be 472.5 at 37 degrees. So now that we've got our scalars multiplied in, it becomes the type of problem that we've already done. Now we just want to add those two vectors together. Okay, well, let's find the x components of our resultant. The x component of the resultant is going to be 2233 times the cosine of 220. That works out to be, again, leave more sig digs than what you need here until we're done. 2233 times the cosine of 220 is negative 1710.6 plus 472.5 times the cosine of 37, 377.4, which gives a net x component of negative 1333.2. Okay. All right, well, the y components. The y components are, let's see here, 2233 times 220 is negative 1435.3.